So the next speaker, I want to introduce you to Adam Carroll. Adam is from Western Australia. He completed his PhD in plant biochemistry at the University of Western Australia in 2008. From 2009 to 2017, he continued this line of research at the Australian National University. I'm not going to read the rest of it, you can read it. But I do want to read this bit. After hours, Dr. Carroll works as a volunteer with the Southern ACT Catchment Group to do bushland restoration work and develop a new volunteer-driven citizen science platform using a drone to map and monitor bushland ecosystem of degraded former farmlands in the ACT by Park Care. That question was asked of the Minister last night, so maybe that questioner could mail Adam after his presentation, and you might get some more information from Adam. So I want to introduce you to Adam Carroll.
Many thanks, Charlie, and hello, everyone. Where's our slide progressor? Do we have a keyboard? Sorry. It's just the green button. All right. All right, so today I want to talk to you a bit about, it's a bit of a solutions-focused talk. I'm a bit of a techno-optimist. Danny asked me to talk about dealing with climate change and some of the potential, good news, glimmers of hope. So I'm going to talk about potential technological solutions to the impending food crisis. So I won't go over this whole slide, but basically I'm a sort of biochemist, molecular guy, a mass spectrometrist, plant scientist. I like to think about mechanism and plant responses to stress and how we can use those understandings to feed ourselves, among other things. So I'm going to focus a lot on wheat because it's a major crop in Australia, and it's one of the main food suppliers for humanity. And it's under threat from climate change. And we need to, there's various papers, about rising food demand and population growth, and they have different estimates on the amount of increase in demand that we're going to need. But basically, we need to double food productivity in terms of yield per hectare, roughly speaking, by 2050, which is a huge undertaking, as I'll talk about in a moment. And achieving that is going to require radical changes to the way we do agriculture, including regenerative approaches, in my opinion. So population's growing. The amount of arable land is going down and land's getting degraded, and the people here are helping to ameliorate that problem. But population is growing, and this graph is showing you the difference between our projected growth in yield, but between now and 2050, and what we actually need. So we really need about a twofold increase in the rate of yield gain for wheat, and we're only achieving about half of that at the moment. So something needs to happen to increase the rate at which we're improving our productivity. And this is in terms of tonnes per hectare. That's just for wheat. It's even more severe in crops like rice. So water limited yield gap. So we saw slides earlier about the decreases in rainfall. But basically, just with current rainfall levels, this map is showing you the average yield losses relative to the full yield potential of wheat if you were to irrigate it. And so most of Australia, well, pretty much all of the wheat growing areas in Australia, their yield is limited by water. And this is showing the average over quite a number of years. But in bad years, we lose almost all of the yield. So there's this massive and increasingly severe problem of yield gap with wheat. That's only going to get worse with hotter and drier climate. So that's not going to help us double our food production by 2050. So rainfall is projected to go down. I'm not a climate modeler, so I can't tell you which of these climate models is the best one. But basically, the point is somewhere underneath all of these dark red pixels showing strong decreases in rainfall is a map of Australia. And this is the most likely, best case scenario with a 2.5 to 3 degree warming. But it gets a lot worse in the worst case scenario. And if you listen to Ian, you probably, I don't want to be a pessimist, but we should be planning for the worst case, I would say, and hoping for the best. So I'm going to talk about some of the usual go-to options that you hear people talking about as ways to solve this problem. So can breeding save us? Well, if you look at gains in yield tonnes per hectare in wheat over the last 50 odd years, we've only seen about 25% improvement. This is a Nature Plants paper showing the temporal trends in gains in yield. So that's not really fast enough. There is a lot of breeding for wheat for drought tolerance is important to minimise the losses that we get with water limitation, and that's going to continue to be the case. So this table showing differences in what we call yield gap-based drought tolerance. So we've just recently published a paper looking for ways to improve the way we screen for this trait, which is yield gap-based drought tolerance is basically the average yield in irrigated, so the yield potential. Sorry, I've got this ratio around the wrong way. Sorry, it's the average yield in rain-fed conditions to the average yield in irrigated conditions. That's the percentage of the yield potential that you see in rain-fed or water-limited environments. So this trait can vary a lot. So there is variation out there, but it's not really improving very, very quickly, not quickly enough through breeding. It's quite slow. The current mechanism, the current methods for measuring YDT in the field is quite slow and expensive, and it's difficult to control. Here's a picture of a field trial out at Yanco. So you can see the scale of the experiments, and this has to be done across lots and lots of different field sites to get field relevant information for the development of new cultivars. And that's just to make sure that the cultivar you end up with has a high yield YDT trait. But it doesn't necessarily mean that you're going to see future massive gains in yield in water limited environments. So we did an experiment to look at whether you can select for this YDT trait in faster experiments in the glasshouse that are cheaper and easier to control. And we found the general opinion among breeders is that whatever you do in the glasshouse has no relevance to the field, but we showed that that's not true. Basically, we got these different cultivars with these different YDT values that were measured in those big field trials, and then monitored their physiological and molecular metabolic responses to glasshouse-based drought. And we found that we got a strong correlation between things like leaf water content early in the drought, correlated very strongly with field trials, as good as any of the measures that, the imaging type measures that they do in the field to monitor for and predict this trait in the field in terms of the R-squared values. So you can select for this quicker in the glasshouse. So because you've got a controlled environment with the glasshouse, you can do these experiments year round. You don't have to just wait for a certain season, and you can control the environment more precisely. You don't need as many plants, that type of thing. So it is a way to speed up this selection. But we also showed that you can use the amino acid responses to the drought stress to improve the predictive performance of the selection. So instead of just looking at leaf water content, you can actually measure the metabolic response. And just with 4 amino acids, looking at how they change in response to drought stress in the glasshouse, we can explain 98% of the field-based yield drought tolerance. So that's great. but is it going to solve the food crisis? Probably not, but I'll give you a bit more evidence for that. So we could speed up breeding using, in University of Queensland, they're doing this speed breeding approach where they can increase the number of generations from seed to seed on wheat by about threefold by growing the wheat under constant lights or almost constant lights in the glasshouse. And that allows them to do line development much quicker, about three times quicker. So that's really great. But is it enough to solve this problem of needing to double our yields by 2050? I'll show you this video if this will work. Here we go. This is a speed breeding time-lapse video showing just how quickly. So on the left, you've got the speed breeding plants growing under really long daylight under lights. They're using LED lights now. And on the right, you've got the normal sort of day cycle. This is a wheat plant coming up. And you're going to see the flag leaf there and then the spike coming up. So it's dramatically increasing the rate you can generate, lines, which is awesome. And what they're also showing is they're confirming our findings that you can predict field traits in the glasshouse as well. So this, that's also really good news. But so can it solve this slow yield gain problem? Well, assuming we can just keep on getting more and more gains in yield indefinitely, is this rate of gain going to be enough from using speed breeding? Well, basically, because the line development stage, done in the field is slower. It's just that line development stage really, and maybe the validation. First, I'll talk about the line development stage. Okay, so if you go from 6 years to 2 years for that step, but you still have to go, if you're ultimately making cultivars to go into the field, you still have to do the field trials to validate that they're going to work in farmers' farms around Australia before you can release it to them. So that step and the release step where you've got bulk up seed and everything to get it out to market still takes a lot of time. So even though you gain a lot on the early stage with speed breeding, you don't necessarily, if you're still making cultivars for field deployment, you're not going to have a huge, you might get a 1.5 times speed increase. Whereas if you're developing cultivars for glasshouse deployment, you get, and you're screening the traits in the glasshouse for the glasshouse, you can also reduce the field, the validation trial step, to optimize the growing conditions and all that kind of thing before you release it. So then you might get maybe a 2.4 times increase in gain speed. So there's a lot of words on this slide, mostly so I can remember what I say, so you don't have to read it. Rapid accurate selection for stress tolerance might reduce future losses, but of course it's not going to restore the degraded land or fix the climate problem. Even you can't grow, even with the most stress tolerant crops, you can't grow and produce yield without any rain. Ultimately, I feel we need to repair and regenerate natural biodiverse ecosystems, ideally to achieve real ecological sustainability. Like, we need to think about feeding ourselves, but also we need to think about all the other animals and plants and their need to feed themselves. I would say regenerative agriculture has a big role to play in that transition, but we should try to find ways to meet the productivity gains that we need for food production, but if possible, reduce the amount of even land that's used for agriculture at all, and ultimately try to reduce the amount of impact on the natural ecosystems. So the next section of the talk, in the next 6 minutes or so, I'm going to talk about some ways to produce food much more efficiently than growing them outside on the landscape in where we would normally have natural ecosystems. So this paper came out fairly recently showing that you can produce wheat in a controlled environment, in a vertical farm, at yield per area, land area, that's about 200 to 600 times that of broadacre wheat farming. So this is a vertical farms, high intense production of wheat in a controlled closed system. Here's an example. So the tomatoes that you buy at Coles at the moment are produced in a system like this. And in South Australia, this is a solar powered, completely off-grid, renewable powered, intensive tomato production facility using renewable energy from solar thermal energy, which is totally awesome. So this is their system. I probably don't have time to go through it, but there's the link there if you want to check that out. But basically, they're desalinizing their own water. They've worked it all out to be really efficient, and they're producing those nice, affordable, and tasty tomatoes you get at Coles. Well, not as good as the tomatoes I grow, but. Another area that's really exciting is this idea of photovoltaic. Well, it's not an idea; it's a technology that's now being deployed at Murdoch University. There's a few competitors, but Clearview is one of the leaders, and they basically made this glasshouse glass that is also a solar panel, but it lets visible light through, so you can still grow plants underneath it. So people usually think of controlled glasshouses as this really energy-consuming, high carbon footprint kind of activities. But if you're using renewable energy and you're being really efficient about the way you use sunlight, and you're using these new technologies, you can actually get the energy consumption or costs of energy very, 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 very low. So that's super cool. I'd really like to see this one at Murdoch University, which is the first in the world. So it's great to see Australia leading the charge in deploying this for agriculture. I love the cheeky grin of Mr. Professor Cheng Dao Li. I've got a lot of glasshouse envy. I really want to go check that out. I'm from Perth, so I'll probably get a chance to do that not too long now. The borders have reopened. So the other thing is about water. So I talked about vertical farming with Rebecca, the Member of Parliament, yesterday, and I said, can Canberra have a vertical farming kind of R&D centre or something? And she said, oh no, we thought about that, but don't they consume heaps and heaps of water? And I'm like, no. So this graph here shows this is a closed system where the transpired water is recycled back into the hydroponic system to keep feeding the plants. So the actual water consumption, in theory, from the perfect closed system is basically the water that you have in your juicy tomato when you eat it. The rest of that transpired water just gets cycled through the system, and all that cycling and thermal control and everything is driven by renewable energy. So you basically have a extremely more resource efficient system to use a closed system like this. So there's different ways of doing this kind of farming. This study that came out recently was looking at comparing the different methods for urban agriculture in Singapore, and concluded that the most efficient way to feed people in that dense Singapore population would be the type where instead of, so it's vertical farming, so it's basically the center one here, number B, where you've got natural sunlight growing the plants rather than sort of enclosed lots of LED lights, because you have losses of energy efficiency along the way when you convert between sunlight to electricity and then back to light again. There's losses along the way. They basically concluded that this kind of vertical sunlight powered system is the way to go, which is good. I'll show that to Rebecca when I go back to her about the vertical farming options. So I've whizzed through. I'll leave it there. If anyone's, I also want to acknowledge other people that have worked with me on some of this stuff. But yeah, I won't keep ranting. Thank you.
Thank you very much, Mark. You're not ranting at all. Just hang on. Listen, I want to say two things. Firstly, remember this publication. Please look it up online on the website of the Sustainable Population Australia Group. Secondly, we're all leaders in this room. And if you think, do and act as a leader, people will listen to you and people will follow you. So take that on board, please, as you leave this forum at the end of the day. I want to really thank the speakers of this session. This session was about dealing with climate change. We have a really important role to play in that as farmers, a really important role but we won't solve climate change unless we stop burning fossil fuels.